Alright, so let's see here. Today I will be introducing some new techniques that Bob and I have been working on for a very classical problem called the dynamic optimality conjecture. So this might be familiar to a few of you. Oh, Mike? Yeah. This work? Okay, so this might be familiar to some of you guys who've seen different pieces of this before. Probably new to most, but let's begin. So the topic of interest today, I'm sure you guys have all seen a specimen of this at some point before, a binary search tree, but just to get us in the mood here, a binary tree is a collection of nodes. One of them is designated to be the root, and every node has two children, left and right, and either or both can be null. And a binary search tree obeys the symmetric order. So every node in the left subtree, every node in the left subtree of the root is less than the item in the root. Every node in the right subtree is greater than the item in the root. And this goes recursively down the tree for every node in the tree. And this structure lets us do a binary search, right? So if I want to find key k, start at the root and go left if k is less than the root, right if it's greater than the root. And you either find k in the tree or you hit a null node, in which case k is not there. Basic restructuring primitive for binary search trees is a rotation, which is essentially an edge flip. It reverses the relationship between x and its parent y. So here I rotate it left child x, and I make its parent y into its right child, and a rotation at y reverses that effect. It changes 3 or 4 pointers, depends on how you implement it. But the idea, order 1 pointer changes, so we treat it as an atomic operation and a unit of cost. And rotations are probably most commonly used or seen in balanced search trees, where you maintain some invariance about sizes of subtrees, and you use rotations to restore those invariants whenever you insert or delete something. But in this case, we're going to use them slightly differently. So splaying is an algorithm that adjusts the tree at every axis. And what you do is you do a binary search. You do a binary search for your node x, and when you find it, you move it to the top of the tree via a sequence of steps, of splay steps, and along the way, it spreads out the nodes along the access path. And the steps are called zig, zig-zig, and zigzag, and they're as follows. So which operation you perform, it depends on the parent-grandparent relationship between, the relationship between x and its parent and grandparent. So the zig case, if the parent of x is the root, that's terminal, so you just do a single rotation and make x to the root. If x and its parent are children of opposite directions, that's a zigzag. And so you rotate twice at x, and you split y and z as its left and right subtrees. And if x and its parent are children of the same direction, then you rotate first at y, then at x, or it's like flipping the two edges at once. And in case this is a little unclear, I think this will help illustrate it. So this is a single splay operation. Here I splay 4 in the tree, and each tree depicted is the application of a single zigzag step. So I start at 4, I split 3, 5, 2, 6, 1, 7. And this splay operation splits the access path. This is a pure zigzag operation. Is this clear? Zig-zig is a little more interesting. This is pure zig-zag. Here I'm splaying one. Each tree depicted is the application of a single zig-zag step. And notice how I get a kind of comb-like structure when doing this, by flipping the edges 1, 2, 3, 1, 4, 5, 1, 6, 7 as a unit. So that is splaying, and you do this every time you access an item. And you can call this an algorithm or a data structure, but splay trees are kind of interesting because, well, they have properties you might not expect intuitively. So the cost of any individual access can be very large. You know, depending on how it restructures the tree, you can get a long access path. So the cost of a single access can be order n, the size of the tree. So that's bad. But if you sum up the total of the access costs, and I should clarify, access cost here is just going to be defined as the depth of the node in the tree, or number of nodes on the access path, one splaying. And right, if I total the costs of all of the accesses, then I get order log n time amortized per access. But it has a whole bunch of other interesting properties. It makes use of spatial and temporal locality in your access sequence. So it costs less to access nearby nodes in symmetric order. It costs less to access recently requested nodes. We're not going to use that stuff. We're not going to use any of those properties of splay trees, but it's just kind of there. They motivate the question that we are interested in, which is whether or not this algorithm is constant competitive in a model for binary search tree algorithms. And so in order to make that question precise, we need to define the model here. Everything clear so far? Great. So the basic operation in our model is going to be subtree transformation. Now this is probably less usual than rotations. It's not as common a way to define things, but it makes things mathematically very nice for our purposes. So the idea is I pick some arbitrary connected subtree of the root Q. I transform it into any other subtree Q prime that I want. I reattach the subtrees in accordance with the symmetric order, and that's a subtree transformation. And the cost of doing this is ascribed to be the number of nodes in the subtree that I chose. So it's the size of the subtree. This is equivalent to doing rotations where I count a cost of 1 per rotation. There's many ways to transform between any two trees T and T prime with a linear number of rotations. And this is just one depiction. So here the method is we transform T, with the starting tree, into some canonical flat tree. Here, like we have a root and it's just a list on both sides. And then to go from this flat list to T prime, we apply what would be the flattening procedure for T prime, but in reverse. So we undo those operations. So you can transform between any two trees like this. There's many, many, many ways to do it. And the cost of a subtree transformation we defined as the number of nodes in the subtree, and we can transform subtrees with a linear number of rotations. So these things are equivalent, but the subtree transformation description of things is going to be a lot nicer for us to work with. OK, so now the model itself. An instance of a binary search tree execution problem is simply a list of requested items and some initial tree containing them. An execution of this instance is a sequence of subtree transformations that successively brings each requested item to the root of the tree. The cost of an execution is the sum of the sizes of the subtrees that I've chosen. Clear enough? Just to make it concrete, this is an example of an execution. The instance is this is the sequence of items 1, 2, 6 contained in that initial tree, T0, and this is one execution of it. And notice how Q1, the transition tree Q1 brings 1 to the root, and I substituted into T0, and Q2 brings 2 to the root, and I substituted into T1 to get T2, and Q3 substitute to T2 to get T3. And that's what executions look like in this model. Straightforward enough. So at least one of these executions is, okay, each of these executions, each execution for an instance has a well-defined integer valued cost. So one of them has a minimum value. So we'll just define the optimum cost of an instance as the minimum possible execution cost for that instance. So that's the optimum in our model. Okay. Yeah.
So do you assume that every time after the access, the item is from the root?
Yes. That is equivalent to you can do it without assuming that it's moved to the root. You'd lose a factor of 2. There's lots of little ways you can change the model and simplify a few things. And this definition of the optimum is within a constant factor of any of a number of others. Another way you can define it is I do a sequence of binary searches, cost of the depth of the node, and then in between each search I can do some arbitrary number of rotations at a cost of 1 per rotation. That optimum cost is within some constant factor of this. Proof of that is a little bit folklore, but it's not that tricky. This is just the model we're using because it kind of treats executions as these nice, well-packaged objects that we can play with directly instead of some sequence of rotations.
But you'll assume that there is an algorithm that will produce these optimal. There's no uniformly sort of assumption.
No.
Undecidable. I don't know, right?
It's not undecidable because
You can try all of them.
Yeah.
For a fixed n. But what if n is? What if your algorithm? I mean, most algorithms work for all n, and they have constant size. But you don't make any assumption like that, right?
Well, correct me if I'm missing.
If you're given the sequence, you just try all possible algorithms.
Right,
and find
but
a number and super
yes,
exponential.
but usually algorithms do not depend on the length. Your space tree algorithm just works for any n. So you don't require.
This algorithm works for any n. It's just
No, but
incredibly expensive.
Oh, you mean, yeah, so this would be exponential in trying out all possible things. But you don't require that there should be there should be some kind of reasonable algorithm that generates this.
Oh, I'm not assuming that this is polynomial time. I'm not assuming. So right now I'm distinguishing between an algorithm
Right. So
and an
it's not
execution.
Yeah.
This is an execution. It's just another word I could use is solution. A sequence of subtree transformations is a solution to the binary search tree problem. And an algorithm maps instances to executions. Now, an algorithm, right, it's any map and some infinite set of such things. And some of those algorithms are going to be nicely computable, like Splay. Some are going to be NP hard, maybe. So, right. But an algorithm just maps each maps each instance to an execution for the instance. Clear enough? Cool.
There's evidence that it's NP hard to find the
Yes.
optimum.
Yes.
There's no proof.
But you're interested in the constant, in the best constant, or is it beyond?
Right now we want something that's constant competitive at all. We want So we want an algorithm where the cost for it to execute the instance is within some constant factor of the optimum. And that constant factor is held fixed over every instance. If you can find some constant where that's true, then
But Bob's comment is that it's NP complete for some small constants.
No, to find the optimum.
Might be NP
Exact
complete.
optimum.
But
So
what
here's
if-
the problem. You got an initial tree, you got a sequence of requests. That's your input. In the size of that, you're gonna compute the optimum.
I get it, but what if you want, you're off by a factor of 2, and you're happy with that? How hard
Well,
is
that's the
it?
conjecture, right?
Yes.
Nobody knows.
So there's the conjecture?
Yes.
The conjecture is that splay is within a constant factor.
The conjecture is that the execution output by Splay, that there exists some constant so that the cost of splaying x starting from t is no more than that constant times the optimum cost. That's the conjecture. No one knows what that constant is. I have my suspicions, but that's the conjecture. Does the conjecture make sense? Right? We have one algorithm, Splay, and just kind of to note, in this viewpoint, we're not viewing Splay as, a procedure for rotations. It just maps access paths to splayed paths, and right, abstractly speaking. Obviously, it has its own significance. Okay. So, what is known about this thing? So there is a data structure that is known to have cost log n times the cost of the optimum execution. And n is the size of the initial tree. And they did this by building a data structure based off of a lower bound. And log n was the overhead that they got with respect to that. There is an offline algorithm, colloquially known as greedy, which is conjectured and generally believed to be optimal as well. And Domain and company turned this into a kind of online algorithm recasting this binary search tree model in a very different way in terms of geometric point sets and finding a satisfied superset of some collection of points on the plane. I won't go into that here, but they use a very different viewpoint of this problem to turn this offline algorithm into an online one. There's a kind of toy meta algorithm, uses weighted majority updates, where if some offline algorithm is optimal in an appropriately defined class, then this meta algorithm is optimal. And there's various lower bounds for optimum executions. And none of them are known to be tight. And in fact, there is no polynomial time algorithm whatsoever that is known to compute to within a constant factor the value of an optimum execution. Online or offline. Online meaning I can't see the requests that come in the future. Offline being that you can. A generalization of this problem where at each request I can ask for multiple items in the tree. That is NP complete. And it's open whether or not this single item per request is NP complete. But it probably is. And on a heuristic level, it's hard to describe it, but opt is a global minimizer. So if I change one of the inputs early on in the request sequence, then the optimum algorithm can go ahead and change all of the transition trees that it chooses to save a little bit on cost. And intuitively, if I change some item in the request sequence by a little bit or change one or two of them, it shouldn't affect the overall cost. But it's really hard to come up with a perturbation style type argument where you would show by successive alterations to the request sequence some bound on optimum executions. And basically, just from personal experience and also throughout the literature, general consensus is that this is kind of a barrier. Understanding the behavior of the optimum algorithm in this model is it's a barrier to understanding. And my approach to this, my first thought when I started working on this was to eliminate that and find a different way to go about it. So the main things that, the main results that we show are we reduce the question of dynamic optimality to whether or not splay is approximately monotone, which in the paper this is called the subsequence property. I've adopted this terminology as it's more fitting. The idea is if I remove items from a request sequence, then the cost should go down.
Strictly. Including removing from in the middle rather than only at the end of the sequence?
Yes. Yes. Yes, or at least the cost should not go up too much at worst. That's what you would hope for. If splay has this property, it is dynamically optimal, and it's a necessary condition for dynamic optimality. And also, this is interesting within the context of other problems related to dynamic optimality, but the techniques are kind of interesting in their own right. Is if splay is optimal, then it won't have any kind of non-trivial additive overhead. So a priori, you might imagine if I start with a bad tree, like a left path or something, then it'll take some time for splay, it'll take some number of splays to get the tree into a more balanced state. And maybe there's some n log n overhead, additive, something like that. That's conceivable a priori. But that actually can't be the case. If splay is optimal for some additive overhead function like that, then you can absorb that additive overhead into the constant factor in front of the optimum. Which is perhaps surprising that you can say something about what, the manner in which an algorithm is optimal while not knowing if it is. But so that's the second thing. The third and fourth things that I'll only kind of briefly cover today. There's a lower bound, Wilbur's lower bound or the crossing lower bound, and that is a monotone function. If I remove items from the request sequence, then the value of the lower bound decreases. And the last part, which is an extensive detail in the paper, is various arguments about how that proof could potentially be adopted to proving that splay is approximate monotone. Cool. So, yes?
So just from abstract nonsense, is there a universal kind of tight dual formulation or a lower bound, or?
You can make these constructions much more general. We might want to talk after for me to say more than that. Right. So an algorithm is approximately monotone if the cost of executing some subsequence is bounded by the cost of the original sequence. There's some constant multiple. And by subsequence here, I mean I don't have to remove a contiguous subblock, right? Just knock out any set of the indices. Okay. And the main tool or construction that we're using here is a simulation embedding. And this is my terminology. So the idea is, an algorithm maps instances to executions. I give you a request sequence, an initial tree, and an algorithm gives me some output sequence of transition trees. And this is a reverse map. So I give you an execution. I give you a sequence of transition trees, and the idea here is to make your target algorithm simulate that execution. And so it outputs another request sequence, and the cost for the algorithm to execute the simulation sequence is bounded by the cost of the original execution. And the other thing is that this simulation sequence contains the original requests as a subsequence. So the original request sequence is embedded as a subsequence of the simulation. Does this make sense?
Right. Is this c times cos of x or c times cos of e?
My bad. E is an execution.
Okay.
So I could write c times q1 plus q2 plus qm, and so on. Right? So this is a general theorem about set-valued functions. Doesn't really have anything to do with binary search trees, except that we're applying it here. But if I have an approximate monotone function with a simulation embedding, then that function is optimal or constant competitive. And the idea is x is embedded as a subsequence of some simulation of an optimal execution for x. So if the algorithm is approximate monotone, then the cost of executing x is upper bounded by the cost of executing the simulation, which is bounded by the cost of some optimal execution. So all we need to do is build a simulation embedding for Splay, and we get approximate monotonicity implies optimality. Is the argument clear? Yeah.
Sorry, what's the simulation again? It was just a little too quick, I guess.
A simulation, well, I guess there's multiple parts to it. The simulation embedding is the mapping, and the map
Back to
takes,
slide.
yes. Oh, yes.
And the map takes.
Okay. The map takes an execution. It takes a sequence of transition trees or subtree transformations. Q1 to Q1 prime, Q2 to Q2 prime. It outputs a new request sequence. This may actually benefit drawing on a board, but
Oh, I see. Okay.
yeah.
So it's just the definition. And then,
Yes,
like,
this is just, this,
okay.
yes.
So it's probably going to be a lot of work to construct this simulation.
Surprisingly not that much, but yeah, presumably lots of stuff can go into that. But to picture it, picture subtrees here and requests here that induce an algorithm to simulate those subtree transformations pictorially. Good? Awesome. So if we construct a simulation embedding for Splay, then we show that approximate monotonicity is sufficient for optimality. So the way to do that is we simply induce Splay to perform each subtree transformation. And how are we going to do that? Restricted rotations, as indicated by the large font here. The main takeaway here is using rotations located near the root. We can transform t to t prime with at most 4n restricted rotations. Rotations where the parent is either the left child of the root or the root itself. And how do we do that? Actually, I've already shown you how to do that because that was the same construction I used earlier. It's just one way to transform trees with rotations. You do this unwrapping, and you can see that each of those rotations take place near the root. This makes sense? We're just doing rotations near to the root in order to transform the tree. Why do we do this? Because we can induce Splay to perform these restricted rotations. And the best way to see that is you take all binary search trees on 4 nodes. 4 is all we need here. And you draw an edge between them if I can Splay at some node in one tree to turn it into the next one. And this is a transition graph, and this is strongly connected. And it has diameter 5. So we can perform some sequence of splays to transform any 4-node tree into any other. And then that kind of acts as a restricted rotation. So in fact, this graph is Hamiltonian. And so how would I do that? Let's say I want to rotate at 2 here. I follow the diagram, splay at a starred node to go from one tree to the next. So I rotate at 2, then I splay 2, 1, and 4, and I end up here. And that's the equivalent of enacting a restricted rotation. And you can follow this graph for any other pair of trees like this. This isn't the most efficient way. I drew it like this because this is pretty and makes the point, but you can kind of do a case analysis and just draw the transition graph directly, and it's diameter 5. So I'm just kind of following this circle to perform each restricted rotation. And this lets us perform subtree transformations because there's 4n restricted rotations to transform T1 into T2. Each of those can be done with 5 of these splays, and each splay path has length at most 4. So I just tally it up, 4n restricted rotations, 5 splays per restricted rotation, 4 nodes per access path, so at most 80 times the size of the tree. And that lets me do subtree transformations. This works for connected subtrees of the root. Make sense? Okay. So this is, right, so then the simulation embedding is simply, I concatenate the sequence of subtree transformations that enacts my target execution, right? And each one of those successively substitutes qi for qi prime in the tree. The cost of each substitution is at most 80 times the size of the subtree. So the total splay cost is 80 times the sum of the subtree sizes, which is 80 times the cost of the original execution, and I can set my execution to whatever I want. So I make it the optimum execution. The only detail here is we need to show that the original request sequence is a subsequence of this thing. We defined our model to have requested items move to the root. So each qi prime has xi as the root. Splay moves whatever it touches to the root, so the last item in each of those transformation sequences had to be xi. So xi is contained as a subsequence of this thing, and the cost of executing that simulation is bounded by the cost of the original execution. So this is a simulation embedding for splay. If splay is approximate monotone, then it's optimal. And as one thing, you might hope that the constant factor would be 1. You would hope that, or you would think that removing an item or removing a request would decrease the cost. This is not the case. Removing a single item can at least double the cost. This one gives an example for 3 halves. So the sequence is splay 3, 1, 2 in this left path. And the subsequence is I just splay 1, 2. So I eliminate the first item. And that gives me a factor of 3 halves. The way the zig-zags work out. You get a comb, so I'm splaying the bottom ends of the comb. You can play with this. You can get the factor up to 2, at least with this example. I conjecture that's tight. I conjecture this is the actual subsequence overhead. I obviously haven't proven that. But yeah, so that's why approximate instead of just standard monotonicity that you would expect. You do need it. All right, and this is a necessary condition as well. And how do we see that? Sort of as a side note, it's not exactly meaningful to try and prove something constant competitive is monotone if your optimum algorithm isn't monotone. But in this case, we can actually prove it. So if I have a subsequence y of x, then the optimum cost for y is less than the optimum cost for x. And the way that you prove anything about optimum executions, if you want an upper bound on an optimum execution, you just exhibit an execution. Every execution is an upper bound on the optimum. So all we need to do is create an execution for the subsequence whose cost is bounded by the optimum for x. So so we form a subsequence by removing the requests corresponding to some integer subset of indices. And so we use that, start with some optimal execution for x, and we just elide together each contiguous subblock of transition trees in Q1 to QM. We elide the contiguous subblocks corresponding to removed requests. And then by union bound, the elided tree has fewer nodes than the total of the subtrees. If that was word salad, basically I do this. Does this help? As in, right, this is some, like these 3 items in a row were removed, so then I just like substitute each one into the next, and just the output tree, Q prime, is the transition tree. Or essentially it's like I applied all of them at once.
If that isn't necessary, the execution for x is already answering the y.
It is formally, because technically, as we define the model, each execution has, each subtree transformation corresponds to one request. So if we're adding in, right, we're answering requests that aren't there. So this just kind of turns the original execution into a valid execution for the subsequence. And union bound means that you're at least one node short. So, sound good? So the optimum algorithm is monotone, exactly monotone. There's no constant factor there. And then it's just straightforward inequality. If splay or any other algorithm is optimal, then the cost of splaying a subsequence is less. Oh, wait a minute. Did I mix that up? OK, there should be a factor of c here, I think. Anyway, bounded by c times the optimum cost. Bounded by c. So cost to splay the subsequence bounded by c times the optimum cost for y. Opt is monotone, bounded by the optimum cost for x. Again, constant competitive, bounded by c times the bounded by c.
So they're just a C on each line.
OK.
Last time.
All right, that's right. OK. Well, anyway, I think we're clear here. Yes? Great. OK. So before moving on, I just kind of want to pause here. So approximate monotonicity. There's no reference to the optimum algorithm here. This is just a question about an algorithm. Right? It's some intrinsic property of splaying. So we've kind of eliminated optimum from the picture here. Yes? So that accomplishes our goal. It's just an intrinsic question to splay. OK. Additive overhead. So, right, I'd mentioned this earlier. Maybe splaying is optimal plus n log n, right? N is the size of the initial tree. Or n log n, we don't know. And this actually is kind of a nuisance to not know the functional form, because the range of an additive overhead can tell you something about potential functions, which can be useful in other analysis. But anyway, there's various reasons we might want to get rid of this. So can this happen? And well, the answer is no. You can't have some non-trivial additive overhead like that.
So if the overhead were n or sublinear, it would immediately go away because you just make b plus 1 or something.
Yes, because the optimum cost is.
Are you assuming something about the number of requests or the tree size?
I don't think it loses any generality. You have to think. So I'm assuming that the starting tree T is the maximal connected subtree of the root containing all requested items. I'm not assuming every item is requested. And that's a fair assumption because you can just throw those out. They would never interact with the splaying. And I'm assuming, I guess there's at least one request, I think. I think that's actually assumed here. But right, under that assumption, the optimum at least has the cost of the size of the initial tree because it has to access everything. It has to access everything at least once.
So is it the same as saying that Splay is optimal for long enough sequences, then it's optimal for
Yes, that's another way to say it. And formally, right, I can be optimal with some additive overhead function g. And the case I care about is when the overhead is intrinsic, right? There's some sequence of instances where the ratio of the algorithm cost to the optimum cost goes to infinity. Right? That's an intrinsic overhead. I actually need some function to absorb it. And how do we prove that, or how do we eliminate this possibility? Well, the idea is, let's say you start with some high additive overhead. You know, G is our additive overhead function. We're going to repeat the request sequence, and each repetition is going to linearly upscale the cost of both splaying and the optimum algorithm. And we just set k large enough, and we can absorb that additive overhead, because this doesn't depend on the length of the request sequence. So we're like amplifying that. And you can't just repeat the request sequence directly. So you take this augmented sequence. I take x and I append to it the transformation sequence that returns the final state of the splayed tree to its initial state. Because if I just repeat x starting from, if I splay x starting from t and then repeat x, I'm starting from a different tree t prime. And I don't know how to relate those behaviors, otherwise I wouldn't need to prove this in the first place. So I just add a resetting transformation sequence. And then if I repeat this augmented sequence z k times, then the cost is exactly k times the cost of z. And cost of splaying z is strictly greater than the cost of splaying x, because x is a prefix. Oh, hold on. Sorry. Wow. All right. Anywho, and the optimal cost for z for k repetitions of z is less than 83 times is less than 83k times the optimal cost for x. Now, why does this arise? So I upper bound optimum by exhibiting some execution. So what I do is I basically concatenate the execution of the optimum for x with, I just take Splay's transition, I just take the Splay paths to execute the transformation sequence. And that's not the best execution, but it's an execution, and its cost is each repetition is optimum cost plus the cost of the transformation sequence plus plus 2t, where that last bit comes from some technical details that aren't interesting to this. But the last point is we can absorb that 82t into the optimum cost. Right? Does this make sense? Great. So then we can just string together the inequalities and eliminate g. So, right, if I have some additive overhead, I can get rid of it. How do I do that? This is the first thing. K repetitions of z is it costs more than k times splaying x. And this is just plugging into the definition of the overhead. And this is independent of k. That's the critical point. This is the second point, upper bounding opt on the repetitions. And then we just set k large enough to absorb the g of t into the constant factor. And looky here, we eliminate the k's. So cost of splaying x is less than 84b times optimum cost for x. There's no additive g of t. And therefore, there's no intrinsic additive overhead, because that ratio is always constant. You can't exhibit something that goes to infinity. So, these things, this is like, all of that was the first half of the paper, and in the last couple of slides, I'll cover the second half. There's this lower bound on the cost of binary search tree executions, Wilbur's bound or the crossing lower bound, and it goes like this. So I use move to root, which Splay is the second simplest algorithm you might think of. For binary search trees, move to root is the simplest. I search for x and I rotate at x until it becomes the root. That's move to root. And right, so I execute the instance with move to root. But before moving the item to the root, I draw a line up to infinity. And I mark every edge crossed by that line. That's a crossing edge. If I count the number of crossing edges, that's a lower bound on the cost of any execution. The proof of that is not something I'll attempt to intuit here. But that's a lower bound. And you can prove that this is a monotone lower bound. Yes?
What is that line again?
I access 8, right? So if I draw the tree on the plane, I draw a line up to infinity. Right. It's the set of edges that contains the requested item in its interval. That makes sense?
So basically, the number of times you alternate in the search path to that item.
Yes. Yes. There's many ways to define it, and they may have different constant factors or additive factors, but it's all sort of the same. So that's the crossing lower bound, and this is a monotone. Yes?
Wait, because the line crossing actually depend on how the tree looks like. So does that depend on execution sequence, or only on the query?
It depends. The algorithm is fixed. I fix move to root, and so given an initial tree and a request sequence, move to root executes it, and then I count the number of crossing edges specifically for move to root. It's a little bit strange. It's like pick some specific algorithm, count number of these crossing edges encountered by that algorithm. That is a lower bound. Yeah. Okay, I guess vaguely, I have to move things to the root. I have to move them out of the way later, and it kind of counts how many things I have to push back out of the way. There's other reasons why you might expect it to be a lower bound. I won't get into that. This is a monotone lower bound, and my interest in it is if you numerically compute number of crossing edges from move to root, and you compare that to the number of zigzag steps when splaying your instance, those things are very tightly coupled, like not just within a constant factor. I think they're equal to within an additive order t or order length of the request sequence. They are very, very tightly coupled, and they have a whole bunch of other relationships between them. And my suspicion is that the proof of the lower bound being monotone can be used as a template for showing the number of zigzag steps executed by Splay is a monotone function with asterisk there. And then also numerically and for other reasons, the number of zigzags should be upper bounded by the number of zigzags. And if you prove those two statements, then that establishes optimality, since right then Splay would be monotone. This is like 5 pages of the paper in one slide, so I'm just kind of putting it out there for those very interested in this. This is not the only simulation embedding type construct for Splay trees, binary search trees. I wasn't aware of these works until like after I'd done most of this stuff, and they weren't aware of each other, so you could say these 3 things, there's 3 independent rediscoveries of this method in dynamic optimality, so maybe it's kind of intrinsic to the problem. Anyway, so there's a different simulation embedding for Splay, uses potential functions, a little more tricky. And there's a simulation embedding type thing for greedy. They don't use that terminology, but that's essentially what it is. And so I guess the main things that I would wonder is, one, does my, do the ideas for adapting this proof of monotonicity from the lower bound to Splay work? Does that actually get you to optimality? Adapting some of these techniques for additive overhead to greedy and other algorithms in this model. And I guess in a broader sense, the constructs of a simulation embedding, if you kind of go through the footwork, they're very general. They really aren't related to binary search trees per se. And I'd be curious, and also just approximate monotonicity, either for sequence valued or set valued functions. I haven't come across them with some amount of scanning, and I feel like they would have more applications than just this. So I'm curious what other people find with that. Okay. Questions?
Yeah, I'm wondering about these the rules for Splay. How robust are they? Like, what if you perturb them randomly? Do you expect the same behavior? I mean, not that you would want to do that, but just are they like magical formulas, or if you kind of...
If you want to perturb it, well, how do you mean randomly? There's a whole rabbit hole you can go down, but...
Complicated rotations, maybe do it 3 at a time instead.
There's a thing like template Splay algorithms, or template-like algorithms. Splay is probably the simplest member of a class of algorithms where I pick a constant window size and look at the binary encoding of the access path above me at each point, and then I transform according to that binary encoding and rinse and repeat until the item moves to the top of the tree. A lot of those have the access lemma, like the similar amortized properties to splaying. And a lot of them should also, this analysis should apply directly to. So in terms of simulation embeddings, the only thing that you need for these arguments to carry through is you need the algorithm, your algorithm has to transform the access path in a manner dependent only on that access path's binary encoding. And its transition graph has to be strongly connected for some n greater than or equal to 3. Any algorithm, any binary search tree algorithm under those constraints is dynamically optimal if and only if it's approximately monotone, and it would be optimal without additive overhead. Any algorithm fitting that description.
So greedy is known to have the simulation embedding, but not the other thing, not the...
Yes, the problem is that this construction here depends very much on being sure I'm at exactly the same tree. Like the split, like at the end of that augmented sequence, the tree's shape has to be T again to repeat. And so in order, and greedy reshapes the tree. It doesn't fit that description. It's not just dependent on the access path. It depends on items in the past and their ordering. And so if I augment an access sequence with these kind of restructuring things, then they interfere with each other. And you have to carry back the constructions for greedy into the binary search tree view to make sure you're actually at the same tree. Because maybe you can just do this entirely within point sets, but it doesn't seem so trivial. I mean, it should be possible. I'm sure it's true, but...
Because,
yeah.
I mean, the Wilbur too, it has a direct connection to greedy.
Yeah.
So
Yes.
I think whatever you're saying about zigzag and zigzag,
Yeah.
it might be
Yeah.
related to.
Yeah.
In your intuition, do you think Splay is monotone?
My intuition?
Yeah.
Yes, it's monotone. The